Combination parallel circuits. This problem looks probably more difficult than it really is. Step one is to just kind of zoom them out. Give us a little bit of real estate to work with over here. And let's redraw them. We're going to redraw them. If you notice, even though there's several resistors, I guess we should name them too. Coming out of this one, that would be resistor 1, 2, 3, 4, and 5. Okay, we're ready to diagram our resistors now. Treating resistors 1 through 3 as a single resistor. And then treating resistors 4 through 5 as a single resistor. Appropriately doing that, we can solve for our cumulative resistance for resistors 1 through 3. 1 over 80 plus 1 over 100 plus 1 over 150 is equal to 1 over the resistance total for those resistors. Total resistance being equal to, total resistance there being equal to 34.3. Now resistors 4 through 5. Treating those appropriately, we have a new resistance there of 48.75 ohms. The voltage of our battery is given, and we're ready to solve for totals, as in total resistance for this circuit is equal to 83 ohms. Total voltage and total current. Using our Verr triangle, total current is equal to our total voltage divided by our total resistance. 0.072 amps. So that means 0.072 amps are working on this end, and 0.072 amps are working on this end. Now realize they get split up across those resistors, but let's treat this as simply a series problem for now. Solving for the voltage for resistors 1 through 3, the voltage drop or potential difference will be equal to, using the Verr triangle appropriately, the current times the resistance. We get a voltage drop of 2.47 volts. Treating the resistors 4 and 5 appropriately, voltage is equal to current times resistor of resistors 4 through 5. Total resistance there is equal to 3.51 volts. Taking time to make sure that we did that properly, our cumulative resistance should equal 6. Therefore, 2.47 plus 3.51, 5.98 volts, which is really darn close to 6 volts. So we can say with confidence, yes, those are the potential differences across those resistors. Now expanding those values back out, for over here, our original problem. Move all this out of the way. We know that 0.072 amps exits the battery and makes its way over to this junction. Now 0.072 amps worth of electricity, or worth of current, will be spread out across resistors 1, 2, and 3. And we'll choose resistors based on relative resistance. Zoomed up on that more so, we can solve for how much current chooses each resistor by using a Verr triangle appropriately. We have previously solved for the potential difference traveling across each of these 3 resistors. The potential difference traveling across each of these 3 resistors is equal to 2.47 volts. So that will hold true for all 3 resistors because potential difference is conserved. Oh, there's barking. The current drop across all resistors can now be solved for. Current drop across resistor 1, we'll use the Ver triangle appropriately. Potential difference across resistor 1, resistance of resistor 1. Current drop across resistor 2, potential difference across resistor 2, resistor of resistance 2, resistor 2. So comparatively, more current flowed through resistor 1 than resistor 2. 0.0309 is a larger number than 0.0247, which should be expected because relative resistance rates. Across resistor 3, the least amount goes there because that resistor has the most resistance. We can make sure that these current values are correct by adding them up. Current across resistor 1, resistor 2, and current which chooses resistor 3 after that junction. We sum those values up and we get a total current value of 0.0721 amps, which is really close to 0.072 amps. So we know, like we said earlier, 0.072 amps worth of current leaves the battery. It chooses resistors at different rates, and then it makes up back here at this junction. And then at this point, if we were to ask you, hey, attach an ammeter here, how much current is traveling at this position here? It would be 0.072 at that particular position. And then it splits again, and a certain amount of current travels this way, and a certain amount of current traveled that way. Now previously in the problem, we've solved for the potential difference or voltage drop across resistors 4 and 5. Potential difference or voltage drop across resistors 4 and 5 we said was equal to 3.51 volts. Now we can figure out how much that 0.072 amps worth of current travels across these two resistors. We can assume that most of it will choose the 60 ohm resistor, resistor 4, because 60 is such a smaller number than 260. There's less resistance there, so more current is more likely to travel through there. The current across resistor 4 is equal to our potential difference across resistors 4 and 5, in this case 3.51, divided by the resistance of resistor 4. In that case, I got 0.0585 amps. We can also solve for the current which chooses resistor 5, potential difference, and resistance. We can make sure we did okay there by adding up those two current values together. 0.0585 plus 0.0135. Now I got exactly 0.072 amps. And we know that 0.072 amps meets back up after this junction here and travels back to the battery.